Hey boys and girls, meteorologist Steve Caparata back with another episode of Cap's Corner Summer Camp, episode 4 for the summer of 2022. A little bit delayed by the 4th of July, but we're back today. We're going to talk all about weather radar. Radar is such an important part of what we do and such an important tool that we use just about daily, especially in our part of the world where we get so much rain here in South Louisiana. Now, radar, believe it or not, it's something we call an acronym. What is that, Mr. Steve? Well, an acronym is a set of letters that actually stands for something else. So radar actually stands for radio detection and ranging. The letters there in yellow make up radar. So radar stands for that. So in essence, what you need to know is that radar uses radio waves. So kind of like you listen to the radio at home or maybe in mom and dad's car, radio waves are important for how we detect rainfall around us. This is what a radar looks like in real life. This is the one in Slidell closest to us. I showed this in a previous lesson earlier on in the summer. But here's how it works. So within that big dome, that big soccer ball looking thing that we saw up on the tower, there is an antenna. It spins around within that dome, and as it's spinning around, it sends out radio waves. That's what this graphic is trying to show, those radio waves going out. And if those radio waves bounce into something in the sky, like a raindrop, that's what this is supposed to be, some of the radio wave gets bounced back to the radar. Some of it gets scattered out into the atmosphere, some gets bounced back, and the radar can then pick up on that radio wave that bounces back and do some math and some calculations and figure out how far away the rain or precipitation is and maybe how heavy it is as well. Very simply, here's the most important thing I want you boys and girls to remember about radar. I like to tell kids when I go do school talks, radar shows us rain. So let's say it again. Radar shows us what? Rain, right? So here's an example. This was Tropical Storm Barry as it was moving across Louisiana a few years back. As we look at this, we're looking at rainfall. One thing to note here, a very simple thing to note. Number one, where you see the shades of green, that's generally where we have our lighter rain. And then when you start to get into the yellows, the oranges, and especially the reds, that's the heavier rainfall. And where you see the red, that's often where we have some of our stronger storms. Now, we've had radar. Radar was actually originally invented in the 1930s. Weather radars came around during World War II in the 1940s. We've been using them for decades. But a few decades ago, we had a new advancement in radar called Doppler Radar. It uses something called the Doppler Principle or the Doppler effect to kind of figure out a little more about what's going on in the sky around us. So let's talk about that real quick. This is going to get a little more advanced, but hang with me and I'll try to explain it to you, okay? So as our radar sends out some of these radio waves, if those radio waves bounce into a storm that is not moving, the space between those radio waves, called the wavelength, is not going to change. Okay, so the radar can tell, all right, the frequency with which I sent out those radio waves didn't change as some of that energy came back to me. That tells the radar that the storm is actually not moving, or the raindrops within the storm are not moving a whole lot, not moving towards or away from the radar. But here's what happens if a storm is moving towards radar. The radar sends out those radio waves. You see the spacing here. What happens to the spacing of those waves as they bounce back off of the storm? If the storm is moving towards the radar, the wavelength gets smaller. There's less space between the radio waves. The frequency goes higher, and the radar can figure that out. All right, if the wavelength changed and it went from what it was here to the wavelength got shorter, those waves got closer together, that means the storm is coming towards me being the radar. And then the opposite is, if a storm is moving away from the radar, we start out with our radio waves. If the spacing coming back is more spread out, then we know the storm is moving away. The frequency is lower, okay? So that's the Doppler effect, the Doppler principle in action. That's how it all works. So why is Doppler radar so important? Well, most importantly, it can help us with things like this, detecting tornadoes and also strong winds. This was a big tornado moving through parts of New Orleans about 5 years ago in 2017. Here's another example of our Doppler radar in action. Now, this is more the traditional view where we're just looking at rain, but sometimes even in the rain pattern on radar, we can get a heads up and kind of a, uh-oh, there might be some trouble when we see something like this. And this was a storm in Livingston Parish also 5 years ago in 2017. But do you see how there's a hook to it? We call that a hook echo. And if we see a hook echo, that can sometimes be a sign of a tornado. And indeed, in this particular case, this was a strong tornado moving through areas around Killian, not too far away from Baton Rouge. What we see here is, you see this bit of a notch? That's where the winds are essentially kind of punching into the storm and then wrapping back around, and we end up with this hook shape. So that is something that meteorologists look for to know that we might have trouble. But Doppler radar not only allows us to see the rainfall pattern, that hook echo, if you will, because Doppler radar uses that Doppler principle, that Doppler effect we were just talking about, and how those frequencies change. It basically can tell us how the winds are moving within a storm. So we have something like this. When you look at something like this, we'll show this on the news sometimes, but it's important to note we're looking at the wind speeds, okay, that's thing number one. But number two, most often when you see something like this, shades of red are to indicate that winds are blowing away from the radar. So in this instance, our radar, let's imagine, because the map's not big enough, but it's somewhere over here. So the winds are blowing away right there where you see the red. And then the opposite is where you see the greens and also the blues. That's where the wind is blowing toward the radar. So again, our radar's over here where you see the greens and blues, the wind is blowing towards. And in particular, if we start to see the reds and the greens next to each other, that's when we know there might be some rotation. A storm might be spinning in essence. And if the reds and greens are really close together, we can sometimes call it a velocity couplet. That velocity couplet can be another sign of tornadoes. So Doppler radar, an advancement in our radars here over the last few decades, has been real important in helping us as meteorologists figure out where there might be a tornado. All right, I want you to check out this video real quick. If you were a little confused on that Doppler effect and maybe how you can see or hear it in real life, I'm going to show you a couple of examples with a car and a train, how you can actually kind of hear the Doppler effect. So check it out. All right, boys and girls, so hopefully that kind of makes a little more sense on that Doppler effect. You hear how the sound changes as a car or as a train is coming towards you, and then as it passes. That's all about how those wavelengths change as something comes towards you, and then as it gets past you. The wavelengths get closer as it comes towards you, and then they get more spread out as it gets away. So the pitch, that sound, it gets higher as something is approaching, and then the sound gets lower as it's moving away. All right, so I told you about Doppler radar. We have another advancement in radar over maybe the last 10, 15 years or so. It's called dual pole radar. So what's going on with that? So what's neat about dual pole radar is it sends out a radio wave, and it does it two different ways. It sends it out one kind of horizontally, flat like this, and then it sends out one vertically. Also, watch, it'll show you here in a second. There you go, you see the vertical. So what's important about that, dual pole radar is giving us some other benefits on top of our Doppler radar. It gives us a better idea of how much rain might be falling or precipitation out of clouds and storms. It's better at telling us the difference between types precipitation, rain, hail, snow, or sleet. Now we have a better idea using this dual pole radar, figure out what might be out there. And it's also really good at detecting what we call tornadic debris, or debris that's been lofted up into the sky by a tornado. So let's talk a little bit about that. Here's how that dual pole works. So typically, if we've got a rain shower around or a storm around that's made up of thousands and thousands, maybe millions of little drops of water. Now, within a storm, those drops of water, for the most part, are very similar in size and shape. And dual pole radar can kind of detect within a storm the things it's bouncing off of. Are they the same in size and shape, or are they different? So in this image here, and it's called, the big phrase is called correlation coefficient, but this is in essence a way we can pick up on debris within a storm, where all the red is, that's saying, okay, all those objects that we're bouncing off of are pretty much the same in size and shape. So as a meteorologist to say, okay, that's largely probably some rain or drops of water. But we have a little bit of an uh-oh here. We've got this little pocket of yellow that I've circled. That's where the radar's picking up on something that's a bit different in size and shape. So if we take that and then we compare it with, I'm going to give you a better example, we compare it with other products, we then can get maybe more confidence, more certainty that there might be a tornado. So here's maybe a better example of that. Now this is out of Missouri. This was from a few years back near Kansas City. So this is that Doppler Radar velocity product, basically where we're looking at the wind speeds, okay? So remember that red means the winds are going away from the radar, green means they're going towards, and you can see very clearly, I think here, we've got the reds and greens together. What does that mean? We've got a strong circulation. Our storm is spinning or rotating. So that's certainly a big uh-oh for meteorologists that there might be a tornado. But then when we take that and we look at that product I told you is called correlation coefficient, and right where we have the spin in the storm, we also have this area where the radar is telling us, uh-oh, we've got a bunch of objects that are different in size and shape. Then we know this is likely debris that's being lofted up into the sky by a tornado. So when you take strong rotation on the velocity product and you see evidence of debris on this correlation coefficient product, then we have pretty high confidence that we have an actual tornado. All right, a couple other things to talk about when it comes to radar. Now, our radar can behave differently day to day. What do I mean by that? Well, the radar beam actually reacts to what the temperatures look like in the atmosphere, how the temperature changes from the ground higher up into the sky. So some days the radar beam, it's always got some measure of bend to it. As it leaves the radar and gets out into the atmosphere, the radar beam bends a bit. If it's bending less than usual, which will have it traveling higher up in the sky, we call that subrefraction. All right, so why is it important to kind of have an idea about this radar bend? Well, we need to know, where we're looking at in a storm, or we maybe even, and I'll show you here in a moment, some examples where the beam gets bent towards the ground, and when that's happening, the radar beam might be bouncing off something on the ground and not rain. So it might look like rain on radar, but the beam is actually hitting something on ground. So when the beam bends more than usual, closer to the ground, that's called super refraction. And then when we have a real extreme example of the beam bending really all the way down to the ground basically, or bending much more than usual, that is called ducting. So in these last two, these are especially important, super refraction and ducting, because that's when we sometimes call ground clutter on radar. So that's where we'll see some colors on the radar screen that might look like rain if you don't know what you're looking at. But for meteorologists, hopefully we're trained well enough and we can recognize, okay, that's not actual rain that we're seeing. That's the radar beam being bent and bouncing off of things on the ground like buildings and trees and other things like that, and not actually bouncing off of clouds and rainfall. Okay, hopefully that makes a little bit of sense. Another thing we have to worry about with radar. All right, so two things to note. Number one, as our radar beam leaves the radar, it's always tilted a little bit. It does not shoot straight out. So it leaves the radar at a little bit of a tilt. The second thing we note is Earth is curved, right? Can we all agree with that, that the Earth is not flat? So because radar, the beam leaves at a tilt, and because the Earth is curved, the farther you get away from the radar, the higher up in a storm we're looking. So when a storm is close to the radar, we're seeing the bottom part of the storm. That's what this is showing here with example A. But when a storm is farther away, like storm B here, because the beam is tilted already above the ground and because the Earth curves, then we're looking much higher up in the storm. So why is that important? Well, as meteorologists, we know if we want to figure out if there's a tornado or maybe real strong winds, it's more important for us to see this bottom part of the storm than higher up in the storm. So a better chance that we'll see a tornado or strong winds within a storm that's closer to the radar than we will with one that's farther away. Because if we're seeing up at the top part of the storm, we might actually miss the rotation. We might be seeing above where that spin is that could make a tornado. One other thing you might see on radar from time to time, you might see some shades of purple. All right, so I talked about some of the different colors. Now, this is when we look at the velocities, when we look at the wind speeds. So again, one more reminder, I'm just going to keep reminding you of these things as we go along, but reds are when the winds are blowing away from the radar, greens are blowing toward. So Mr. Steve, you told us that already. What about the purples, okay? Purple is what we call in meteorology range folding, or sometimes nicknamed purple haze. And because of where Baton Rouge is, we're kind of far from the closest radar. We tend to fall in this purple haze maybe more often than some other locations. So what does that mean? What's going on? Here's what it means. The radar sends out a pulse. It's going out. It bounces off of a storm. And before that pulse makes it back, the radar sends out a second pulse. And now the radar is confused because it sent out some energy. It was waiting to hear back on that first radio wave that it sent out, and it didn't hear anything back before it sent its next radio wave. The second radio wave comes out, and then the radar does get something back, and it's confused. Is that the first radio wave? Is that the second radio wave? And so, in essence, what we do is we paint in that area as purple on the radar to say, we're not sure of what we're seeing there. The radar is a little bit confused, so we have to be careful with that range folding or that purple haze. All right, I just wanted to show you a few cool things now that you can see, a few more cool things you can see on radar before we wrap up. This is called a hail spike. Do you see how we kind of have this spike showing up on the radar out of the storm? When we see this, a spike that's kind of coming out in one direction out of a strong storm like this one is typically a good indication that we have some fairly large hail within the storm. And if for the older kids that might be watching, if you want to Google this, you can also Google three-body scatter, radar three-body scatter, but hail spike is what is easy to remember. So that's one thing we can see on radar. This is pretty cool. Look at this. Looks like a jellyfish, doesn't it? What's going on with this? All right, so this was up around Memphis. We've got some storms. That's what all the colors are showing. But when we get storms, those storms, we've talked a little bit about this in a previous lesson as well. You get all that rain falling out of the storm, right? And then the rain cools the air around it. And it might cause some evaporation too, which sends a lot of air rushing down to the ground. What happens when air hits the ground? It's got nowhere to go, right? So it has to start spreading out. Well, when that happens with some storms, we can get this. We call this an outflow boundary. So that is the cool air hitting the ground and spreading out. And as it does, it kicks up dust and other things in the air. Sometimes can even be insects. The radar This little thin band, that's probably not rain. That's dust and other things being kicked up by that outflow boundary. But we need to track those because sometimes the outflow boundaries themselves can help new storms develop. This was just one of the more dramatic examples I've ever seen, especially with almost that circular appearance to it. We can also see birds on radar. Can you believe that? Look at this. This was about 5 years ago. Watch this loop back again. Look here around Laplace, and you see how it's kind of a circle? So in the morning hours, we'll have flocks of birds. They like to kind of nest under bridges and overpasses, and as the sun starts to come up, they'll start to take off. And if we see these rings that are happening near and shortly after sunrise, meteorologists know that's the radar not picking up on rain, but probably flocks of birds that are taking off. Here's another example. This is from 2015. Watch this play back, but you can see numerous spots where they were taking off around South Louisiana. Sometimes we call them roost rings. So there's a couple of things. Number one, we know that the birds like to take off around sunrise. Also, around sunrise, our radar beam tends to, you remember some of those different things we talked about? It tends to bend down a little more in the morning hours, sometimes because we have a temperature inversion. That puts a lid on the atmosphere, kind of traps the radar beam closer to the ground. So we see things a little closer to the ground often in the early morning hours. So that makes it easier for us to see birds as well. Not only birds, how about bats? Watch this. This is in Texas. Look at that. These are bats taken off from caves in Texas. Pretty cool, right? And then this is something called a flying eagle supercell. That's just kind of a signature of a really strong storm. I don't want to get into that too much. But these rings are bats taken off in Texas. So we can pick up on lots of things with radar. All right, hopefully you learned a little bit about radar today. One more time. Radar shows us what? Rain, right? That's the most important thing I want you to remember. It shows us precipitation, many other things we talked about, but most importantly, most of the time in South Louisiana at least, we talk about radar. I'm talking about showing you guys rain. All right, coming up next week, we'll be back on Monday next week at 10 o'clock. We're going to talk about satellites. One thing we can see with satellites, you can see right here, hurricanes, but I'm going to show you much more about satellites and how they work. So be sure to come back next Monday at 10 o'clock. We'll talk all about that. But right now, we're going to go ahead and hop into the studio and take any questions you have. So if you have some questions, pop those in the comments on Facebook. All right, boys and girls, hopefully you learned a little bit about weather radar today. Wrapping up lesson number 4 here for Cap's Corner Summer Camp. If you've got any questions, you want to pop those in on Facebook or have mom or dad help you out with that. We'll spend a minute or two answering some questions. This was a good one that came in from Erin. So she says, what does one do if they're colorblind? Does that mean they're not able to be a meteorologist? Great question, because in weather we do kind of rely, whether good or bad, we kind of rely on red and green a lot. Some of the colors that are difficult for people that are colorblind or have some of those visual issues. So no, it certainly doesn't keep you from becoming a meteorologist. There is software that's available to install on computers that will kind of convert those colors into a palette that's more friendly for those that do suffer from color blindness. So there are ways to work around that. And you know, is it something we need to address on our side? Quite possibly so. You know, we're kind of rooted in the way these things have been displayed for decades now. Weather radar has been shown on TV and local broadcasts for decades, and weather apps, and some of these color palettes are pretty standard, so it's kind of a hard shift, but it certainly does not prevent one from becoming a meteorologist. So when I talk specifically about the red and green, when we talked about looking at the velocity or the wind speeds there in the storm, there are pieces of software that will convert that into colors that are more easy for those to see who might suffer from color blindness. All right, let me see if we have any other questions rolling in. While we do that, let me pop up and remind you that on our website, wafp.com/capscorner, all the lessons, once they're completed, the videos are posted here. There are also some worksheets that go along with each of the lessons. So again, this is the 4th one for this summer. So later today, should have that video posted here on this website. Got a couple of worksheets to go along with it, a word search, and a quick little quiz for the kids, or maybe even the grown-ups if you want to check it out. It's 7 or 8 questions, nothing too difficult, and all the questions on that quiz are from the presentation I just gave there. All right, not really seeing any other questions roll in, so let me come back on camera here. In the meantime, you heard it there a minute ago. Next week we'll be back. We'll be back on Monday next week. We had to kind of postpone this week with the 4th of July falling on Monday, but we'll be back next Monday, 10 o'clock, same place, and we're going to talk about weather satellites. So really 2 key tools we use here in weather. Radar, we went over that today, which, as I said, especially for the kids, radar shows us rain, right? Most importantly, shows us rain. Satellites more about clouds. And satellites are really important because, especially this time of year, they're real good for tracking our hurricanes, because satellites pretty much cover the entire globe for us, but certainly cover all the tropics and the ocean, so we can watch these storms for days in advance as they approach. So we're going to talk about the different types of weather satellites, the different types of satellite imagery, different types of satellite pictures, if you will, and some of the neat things you can see on satellites. So be sure to tune in next Monday at 10 o'clock, and just taking one more peek down just to make sure we don't have any more questions rolling in. But as a reminder, you can watch any of these lessons on our website, wafb.com/capscorner. They're also on WAFB Plus. That is our free app for Amazon Fire, Roku, and Apple TV. And also they get posted on our YouTube page. So several places to watch them. But I hope you enjoyed today's lesson on weather radar. We'll see you back next Monday to talk all about weather satellites.